Topic 10, equilibrium. Now, dynamic equilibrium. You remember from IGCSE that obviously you need a reversible reaction. If you've got a closed system and the reaction is reversible, if you leave it for long enough, it will reach equilibrium. It might be very, very slow, but it will get there in the end. So, essentially, dynamic and equilibrium we need to define, don't we? Okay, so when it reaches equilibrium, the forward and reverse reactions are taking place at the same rate, and this is the thing that always causes a bit of trouble, the concentration of each of the species remains constant. They're not the same. It's not like a physics seesaw moments experiment. You might have much more of the products and very little of the reactants left at equilibrium. So the equilibrium can be very heavily to the left or to the right, or it can be somewhere in the middle. It can be pretty similar, but it's important to get that clear. So the forward and reverse reactions are taking place at the same rate at equilibrium, and if you take a snapshot, the concentration, the amounts of the reactants and products are constant. Okay, this is dynamic equilibrium. Look at the example here. If we started with just hydrogen and iodine, notice that they're both gaseous, so we're going to have to do this at a relatively high temperature. But if we start with, why? Because iodine is a solid at room temperature, isn't it? And it's a purple vapor when we heat it, so it would be a purple gas if the temperature is high enough. So if we started with just these two things, then initially they would start to make this hydrogen iodide. However, as the concentration of hydrogen iodide increases, then the reverse reactions rate would increase. So this is where rates and equilibrium, they overlap. There's an area of overlap between the two topics. So the generic equilibrium A plus B making C plus D. Okay, at the beginning, the concentrations of A and B were at their maximum, and C and D at their minimum. And then as the reaction goes on, obviously A and B start to get used up. If A and B are used up, then obviously the reaction rate decreases. Why? Because reaction rate is dependent on concentration. So the concentration of A and B is decreasing, so the reaction rate is decreasing. As C and D's concentrations increases, then the reaction rate, the reverse reaction rate increases. So it looks like this, doesn't it? The reaction rate, the reverse reaction rate increases as the amount of C and D increases. At some point, the rates must become equal. At some point. Now, I would question these being straight lines, but we're not worried about that. The concept is the important thing here. Yes, the rates become equal. This becomes this green line because at equilibrium, the forward reaction and the reverse reaction are happening at the same rate. Okay, that's a little introduction to that. You've got some questions. You've got a couple of pages to read through. Let's start there for today. Anything else on this slide? Not really, no. So many examples of equilibrium around us. There's a queue at Carrefour, and inside the shop there are something like, I think, 50 or 60 people allowed, and outside the shop there's usually about 10 people in the queue. So as one person comes out, one person goes in. Okay, so that's a dynamic equilibrium. There are 60 people inside, there are 10 people in the queue, and there's a movement of people as one person goes, or one person comes out, one person goes in. So there's a dynamic equilibrium in that there's a forward reaction and a reverse reaction, But overall, there are 60 people inside and 10 people outside, and those two figures remain constant. Okay? Have a go at the questions.